Good afternoon. My name is Sandra González. I'm from University of Málaga. First of all, I would like to thank all of you for coming to this talk, whose title is Desirable Objective Ranges in Preference-Based Evolutionary Multiobjective Optimization. In this presentation, my colleagues Rubén Saborido and Ruiz, Mariano, Luque, and me propose a new preference-based evolutionary multi-objective optimization algorithm. To start with, this is the structure of my presentation. Firstly, I will briefly introduce the multi-objective optimization file and the motivation to propose a new preference-based evolutionary multi-objective optimization algorithm. Then, in section number 2, I will describe some basic concept and notation about this file. In section number 3, I will define the new preference-based evolutionary multi-objective optimization algorithm, and then I will design the computational experiments and the result. Finally, I will summarize the main ideas of this presentation and the future research lines in the conclusion section. Well, the multi-objective optimization problems are problems optimizing several conflicting objectives at the same time. Usually, there is no unique solution that achieves the individual optimum at the same time. So, the so-called Pareto optimal solution are defined. In this solution, one objective can be improved without degrading at least one of the others. All Pareto optimal solutions comprise the Pareto optimal set in the decision space and the Pareto optimal front in the objective space. In order to solve these problems, we are going to focus on evolutionary multi-objective optimization algorithms. These algorithms solve this problem by generating a set of non-dominated solutions to approximate the Pareto optimal front. This approximation should be as uniformly distributed as possible in the Pareto optimal front and close enough to the Pareto optimal front. In particular, the decomposition-based IMO algorithms transform the original multi-objective optimization problem into a set of single objective subproblems. Within this type of algorithms, we can distinguish the NOAD, NSGA3, global WASGA, and its improved version, AG WASGA. Given that all solutions generated by an evolutionary multi-objective optimization algorithm are equivalent in a mathematical sense, we introduce the concept of a decision maker. A decision maker is a person expert in the problem domain, has to be involved to express his/her preferences to localize the most preferred solution as the final solution to the problem. In order to facilitate the decision-making task, some preferences are included into the algorithm procedure in the so-called preference-based IMO approaches. Some examples of these approaches are WASGA and IRA-IMO. The main purpose of this type of algorithms is to approximate just the set of solutions which correspond to the decision maker preferences. This set of solutions is called the region of interest. In IRA-IMO, an internal algorithm is used called modified WASGA. This algorithm approximates the set obtained as the union of the regions of interest defined by 2 points separately. Knowing this, we propose a new preference-based evolutionary multi-objective optimization algorithm called evolutionary algorithm based on ranges for the objective functions, and its abbreviation is EROF. In this algorithm, the preferences are included as desirable ranges for the objective functions using 2 reference points. The first of them is an aspiration point, and the second one is a reservation point. The main idea of EROF is to approximate the ROI that includes the Pareto optimal solution which belong at the same time to the ROIs associated with both points, aspiration and reservation point. Now, I'm going to describe some basic concept about multi-objective optimization file. A multi-objective optimization problem can be defined as follows: minimizing or maximizing a set of k objective function over a feasible region denoted by S. The feasible objective region is denoted by Z. In this type of problem, a solution is said to be Pareto optimal if there is no other solution that verifies this inequality for all of objective and this strict inequality for at least one objective. The corresponding objective vector of a Pareto optimal solution is called Pareto optimal objective vector. The set of all Pareto optimal solutions is called Pareto optimal set, and the set of all Pareto optimal objective vector is called Pareto optimal front, and its abbreviation is PF. Well, in order to work with preferences, we define the definition of a reference point. A reference point, denoted by Q, is a point in which each value corresponds with a desirable value for the objective function. These values are given by the decision maker. We can distinguish two types of reference point. The first of them is a achievable reference point. This point, in this case, the reference point is in the feasible objective region, or the reference point is dominated by a Pareto optimal solution. While an achievable reference point, in this sense, the reference point is not in the objective feasible region, or the reference point dominates a Pareto optimal objective vector. Well, in order to obtain the Pareto optimal solution of a multi-objective optimization problem, we use an achievement scalarizing function proposed by Verbitsky. The achievement scalarizing function is defined as follows, in which Q is a reference point, mu is a weight vector with all components positive, and rho is a positive real value. If we minimizing the achievement scalarizing function proposed by Verbitsky over the feasible region of the original problem, we can obtain the Pareto optimal solution of the original multi-objective optimization problem. So, in our proposal, the preferences are included by desirable ranges for the objective function by means 2 points, aspiration point and reservation point. And an aspiration point is formed by the values that the decision maker considers as desirable for the objective functions. I mean, values to be achieved. On the other hand, a reservation point comprises the values that the decision maker considers as acceptable for the objective functions. I mean, values about which the objective functions are not admissible. In this graphic, I show you different situations for a B-objective minimization problem, where the region of interest is the region of the PF in blonde. In this figure, we assume that the aspiration point is unachievable and the reservation point is achievable, which is the most logical situation when a decision maker provides desirable ranges. So knowing that, I will define the new preference-based evolutionary multi-objective optimization algorithm. I say before, this algorithm called evolutionary algorithm based on ranges for the objective functions, and its abbreviation is EROF. The main idea of this algorithm is to approximate the region of interest defined by the desirable ranges for the objective function given by a decision maker. And the way to proceed of the algorithm is the following. Firstly, we internally find an approximation to the region of interest defined by the reservation point. Then we update the weight vector according to the specified desirable ranges for the objective functions. And finally, the algorithm employs the new weight vector and the aspiration point to obtain the final approximation of the region of interest. To be more specific, the requirements of the algorithm are the following. EROF requires the desirable ranges for the objective functions given by 2 points, the aspiration points and the reservation point. Also, EROF requires a set of weight vector, indeed, the population size, and finally, the number of the total generations. The number of the total generation is divided into numbers. Firstly, the ng sub 1 and ng sub 2. Well, the main step of this algorithm are the following. EROF in the first ng sub 1 generation performs as in the original WASGA, considering the reservation point as reference point and using the original wave vector. Then, when we obtain an approximation to the ROI associated with the reservation point, the algorithm updates the weight vector in order to orientate the projection direction onto the region of interest. Firstly, the algorithm only considers the objective vector that dominates the reservation point in the step 1. Then we identify the extreme points. These points are the objective vector with the minimum value for each objective function. And then we calculate the strength weight vectors. This weight vector as calculated as follows. Depending on if the extreme point are lower than or higher than the aspiration point. So using this formulation, we calculate the new weight vector as follows. The last step of EROF is to approximate the ng sub 2 generation as in the original WASGAT, using the aspiration point as reference point and the new weight vector calculating in the step 2. So doing that, we obtain an approximation of the region of interest given by the desirable values for the decision maker. In order to measure the performance of this algorithm, we design a computational experiment. We compare the EROF algorithm with NSGA3 and NOAD. We use the test problem from the well-known families as DTLZ, UF, WFG, and ZDT. We use problem with 2, 3, and 5 objective functions. The population size used is the following, depending on the dimension of the problem. The maximum number of generation is 100. The reservation and aspiration points are used for each problem have been randomly generated. And in this algorithm, we use the 70% of the total generation associated with the reservation point. points. So NG sub 1 is 240 and NG sub 2 is 160. In order to measure the algorithm performance, we use the hypervolume metric. So in the following tables, I show you the results of the computational experiment. In these tables, we show the hypervolume mean and the standard deviation values over the 13 dependent runs. The algorithm with the best hypervolume mean is highlighted in dark gray color, and the second best mean value is light gray color. And also we provide the number of problems in which the hypervolume metric is in which error is significantly better than denoted by a black triangle, equal to or worse than denoted by a white triangle, than the hypervolume mean of the rest of algorithm. So in problem with two objective functions, we can say that E of is better than NOAD in 18 problems. Regarding NSGA3, we can say that E of is better than NSGA3 in 15 problems. Considering three objective function problems, E of wins in 11 problems in contrast to NOAD and NSGA3. Finally, considering 5 objective function problems, we can say that E of is better than in 9 problems in contrast to NOAD and 11 problems in contrast to NSGA3. Well, also, we show some final tables in which we provide the p-value obtained in the Wilkinson test and the effect size for each problem. The magnitude of the difference between two algorithms is measured using the non-parametric effect size measure cliff and denoted by delta. I show you if the effect size is small, medium, or large. So for three objective function problems and for 5 objective function problems. So just to conclude, we propose a new preference-based evolutionary multi-objective optimization algorithm. The new algorithm is designed to approximate the ROI of the Pareto optimal formed by the Pareto optimal solution, whose objective values are within the desirable value ranges given by the decision maker, and basing on the result, E of has generated very promising result in contrast to some well-known algorithms like NSGA3 and NOAD. As future research line, we want to make a sensitive analysis of the parameter NG sub 1 in the algorithm E of, and we want to investigate how the algorithm performs dynamically adapting the weight vector while the algorithm converges. So thank you for your attention. These are some references used in the presentation, and thank you for your attention.
Thank you, Sandra. Very nice talk.
Thank you.
Let's discuss a bit about it.
Okay.
Yeah, okay. Are there questions? I see Jose Maria raising.
Yes, I have a question.
Okay.
So first of all, thank you for your presentation and congratulations for your work, first of all. And then let me see if I understood it correctly, because it was a lot of information for me, but just to make it clear, the decision maker is the one who defines the reference point, right?
Okay, see.
Yes, and being that the first step of the algorithm, right?
Yeah.
Don't we have, and by we I mean the algorithm, need to know the Pareto front a priori?
Not is necessary.
Because it will be, as I understood, it will be a combination of the reference point and the aspiration points in the future with the Pareto front, right?
Sorry, I don't understand you. So the algorithm needs two reference points, an aspiration point and a reservation point that are the desirable ranges given by the decision maker. But the decision maker not necessarily know the Pareto optimal front of the algorithm before to solve the problem.
Yes, exactly. But the Pareto front, it's desirable, and the algorithm will ideally combine the solutions to the Pareto front, right? Approximate.
Yeah.
That's where my question comes from, is because it's where how do you intercept the decision makers' points, the aspiration points and reference points with the optimal solutions or the quasi optimal solutions?
Okay. Okay. So we are using the achievement scalarizing function that I showed previously. This is achievement scalarizing function use the reference point provided by the decision maker. So using this achievement scalarizing function, we project with the weight vector to the Pareto optimal front. So using the reference point, we I don't know what to say.
Okay, it's just merely
we bound the Pareto optimal
it's
front.
a directional point, right? Just a guidance.
Yeah.
Okay, that's just what I wanted to clarify. Okay, thank you very much, and
You're welcome.
congratulations once again.
You're welcome.
Excellent. Sandra, could you just report a bit more about the performance or the CPU cycle time or the requirements for your algorithm? I understand that all these higher dimensional multi-objective algorithms are quite time consuming CPU wise.
Yeah, we use in this paper, we use a problem with 2, 3, and 5 objective function objective functions, but we know that now the many objective optimization problems are the more promising problem, but it's very difficult to a decision maker provide values for many objective functions. So in this type of algorithm, we only use a problem with less objective functions. I don't know if this is the question, but I understand more or less.
Yeah, well, I mean, yeah, indeed, it is a quite an ask for someone to define in 10 dimensions or whatever the number of dimensions is. So that's nice that you mentioned that. That's important. But I guess, maybe let me turn the question differently. How does it scale with the number of dimensions? Do you know anything about that, or is it not yet known?
No.
The scaling with larger dimensions.
No, we don't manage this type of problem.
Okay.
In my colleague and me proposed an algorithm the last year that manage 15 objective functions, I think, but it's not a preference-based evolutionary multi-objective optimization algorithm.
Okay, I see. Yeah. I guess it becomes much more challenging after 10 dimensions. So if you have something for 15, that's already pretty good.
Yeah.
Yeah. Okay. Thank you.
Thank you so much.
More questions? Is there any more questions?
Well, actually, I have one. Sandra, can you go back to the slides where you present the effect size, because you went very fast and
Yeah.
it was difficult to understand.
Yeah.
What are the different symbols? Can you? I think it's on the previous slide, maybe.
In this black this triangle, it means that year of our proposal is better than in this problem, in contrast to this algorithm, the NOAD. And the effect size of the differences between the hypervolumetric in our algorithm and this algorithm is large.
Okay, I got it. Now I got it. So the effect size is on the right. It was so fast that I wasn't able to see it. So
sorry.
In lots of circumstances, just glancing of it, the effect size is quite large. I didn't grasp that before.
Yeah,
Very nice work. Okay.
Excellent.
Okay. That was the clarification I needed. Impressive.
Good.